Working safely with electricity. Part 3, the importance of grounding.
Right, thanks a lot. In the last program, you looked at how to dress safely while working on electrical systems. And you saw that power lines directed to a conventional home environment are dangerous and should be treated with extreme caution. In this program, you'll be shown what grounding is, and you'll see how to locate the grounded side of an incoming power line. You'll also look at some of the hazards presented by chemicals commonly used with electrical systems. Grounding. You hear about it all the time. Maybe you understand what it is, but it's such an important feature of electrical circuits that it's worth taking a minute to review. Grounding is a safety feature built into circuits to prevent you from getting injured. A circuit doesn't require grounding to carry current, but without grounding, no circuit can be safely serviced. Let's look at how it works.
In every circuit, current flows from an energy source through a load, in this case a light bulb, and back to the source. The wire from the energy source to the bulb is the hot wire. An ammeter placed across the hot wire will measure the current flow in amps, and a voltmeter will measure voltage approximate to the source voltage. The wire from the bulb back to the source is the neutral wire. An ammeter placed in series across the neutral wire will measure the same amperage as the hot wire. The source voltage has been dropped across the load. This is why this wire is called neutral. Because the neutral wire does carry current, it can, under certain circumstances, be just as dangerous as the hot wire. Here is how an ungrounded circuit can be dangerous. If, through a fault in the circuit, the hot wire contacts the frame or housing around the bulb, the frame becomes live. Now the technician can be shocked by touching the frame. A ground wire is attached to the frame of a component. In this arrangement, even with the hot wire touching the frame, the technician is protected. Now if he touches the frame, the ground wire will protect him from injury.
When power lines terminate at a home or building, electricians need to distinguish between the hot or energized side and the ground side of the wiring system. To do this, electrical wiring is color-coded. The neutral conductor is always white or gray. Ground wires are bare or green. Hot wires can be any other color. But to be safe, don't assume that electrical wires are coded correctly. Occasionally, mistakes are made during installation, or in some cases, wiring has been altered after installation. Always use a meter to test a circuit before touching any wire. In some cases, the ground connection in a wiring system is improperly made. Anytime you work on an electrical system with a faulty ground connection, you're at serious risk.
For example, consider a worker whose metallic drill bit accidentally contacts a hot wire on the job. With an intact ground connection, current will complete the circuit by flowing through the drill bit and exiting through the ground connection. But with an open ground connection, current will follow a different path. Since there is no convenient path to ground in the wiring, current is drawn to any other available ground. Unfortunately, this means current must travel through the worker as it flows to an earth ground. Improper ground connections are extremely dangerous and, when discovered, must be immediately repaired. Never work with equipment that is improperly grounded.
Fortunately, a worker doesn't have to become part of the circuit to reveal a faulty ground connection. Some modern electrical wiring systems are equipped with a ground fault circuit interrupter, or GFCI.
This type of circuit measures the amount of current flowing through the hot wire and the neutral wire. Normally, current flow is the same in both wires, but a short will create an increased current flow on one side of the circuit. The GFCI senses this imbalance, and if the difference is greater than 6 milliamps, it shuts off the flow of current. Ground fault circuit interrupters provide additional safety through a test mode feature. Pushing the test button on the outlet places a short in the circuit. This short should trip the ground fault circuit breaker. If it doesn't, the circuit has no ground fault protection and should be immediately repaired.
But remember, the test mode only protects you if you use it. Take advantage of this safety feature and check the ground fault protection system regularly. Ground fault protection prevents injury by isolating electrical energy away from someone working on a circuit. Other circuit testing devices allow you to analyze current and voltage outputs by making the test device part of the circuit.
Electricians commonly use a multimeter or solenoid-type tester to analyze circuits. Other types of meters are often used in the classroom. The type of meter you use should depend on what you're attempting to test and the voltage level of the circuit you're testing.
Select the test equipment you use to analyze a circuit with great care. Modern equipment is designed to protect you from getting injured. Look for built-in safety features when you select a meter. Since a meter may be your only defense against injury, quality is more important than cost when you choose a meter. Now, without question, the safest way to service electrical circuits or equipment is to isolate them from the source of their electrical energy.
This is generally accomplished by turning off the main power switch to the circuit. You can't get shocked if power isn't available to flow through a circuit. But once you've begun working, you're extremely vulnerable in the event someone turns the power on again. To prevent this, electrical workers have developed a lockout-tagout procedure. Before beginning the procedure, make sure the circuit or equipment to be isolated is supplied by only one power source. An electrical blueprint will provide information about power supplies. Next, notify anyone who might be planning to use the circuit or equipment that a lockout is scheduled. If equipment is operating, turn it off. If there is stored mechanical energy, for example in springs or rotating flywheels, make sure the energy is dissipated or the equipment restrained. Now turn the main power switch off. Use a lock to hold the switch in the off position. Or, if a power box is used, lock the power box closed so the switch is inaccessible. Tag the switch or power box to indicate that it is being serviced, who's servicing it, and that no attempt should be made to open the lock. Before working on equipment, turn its power switch on and then off as an added safety check to guarantee it's been completely isolated from electrical power. Use a meter to test the circuit before touching any wires. Now you can safely service the system. If, for any reason, you leave the area before work is completed, test for power before completing the job. When you're finished, make sure you remove all tools and service equipment before removing the lock and restoring power to the circuit.
What I did find was that the second or third day in the hospital, they were talking about possibly having to do facial grafts, and they had taken me into the scrub room and were scrubbing dead and skin off my face, and what they thought was a strip of barely burnt skin turned out to be the plastic band of my hard hat and melted into my forehead. And when they removed that, they subsequent to that, they determined that in fact I probably would need no facial grafts, as in fact I ultimately did not.
You go through a whole series of feelings, and I was preparing myself for the amputation. And it wasn't up until about the 6th or 7th operation they told me, we feel pretty confident you're going to keep your arm. They don't know how functional it was going to be, but I was going to keep the arm.
But in any case, I had 17 days in the burn unit, and then I had another 11 or 12 days on a rehab floor. So I spent a total of 4 weeks in the hospital, and then they gave me no breather. I got out on I believe a Tuesday, which means it was exactly 4 weeks. Got out on a Tuesday afternoon and had to come in Wednesday morning to begin therapy.
Somebody knocked me in the hand, my arm. I would be in severe pain. And now I can move my arm, and it works pretty decently without any pain. It's still an effort to move it because I lost the biceps and a lot of other muscles, and mentally, it's still the acceptance of the loss of the arm. Yet I'm still a viable person. I have a brain and I can do other things. That's realistically, but when you get down to it, something was taken away from me that I enjoyed. I enjoyed being a lineman. I liked the job, and it was snatched away from me. It wasn't my choice to change professions. It was done for me, and you kind of miss that. You like to be able to control a little bit of your life and say, well, this is what I want to do now as you're getting older.
Getting shocked by current isn't the only hazard associated with electrical systems. Certain chemicals present in circuits or electrical components can be very dangerous.
A common example is lead, used for soldering and wire coating. Lead is poisonous and should be handled with caution. While soldering, never place lead material in your mouth, and always keep your face a safe distance from the point of solder. Dangerous chemicals are present in several different types of batteries. Small, low-voltage batteries often use mercury cells. Cutting these batteries open and handling the mercury can be a hazard to your health. Automobiles commonly use a lead-acid battery that is easily mishandled. This battery is made of cells, separated by lead and filled with sulfuric acid and water. Sulfuric acid is a poisonous, corrosive fluid. It can burn the skin and can cause blindness. Many car batteries manufactured today are sealed to prevent direct contact with sulfuric acid. Many modern electronic components, like capacitors, are made of materials that can be hazardous. Never disassemble electronic components. Taking these components apart can expose you to dangerous material. For the same reason, check with the Environmental Protection Agency to determine the appropriate place to dispose of electronic components.
That's fine. I will make sure that's disposed of properly.
Sometimes chemically active components, like carbon tetrachloride or benzene, are used as cleaning agents. These liquids are effective cleaners, but they're also potentially harmful. Never use toxic fluids to clean. Be certain to check the label of any cleaning agent to make sure it doesn't have toxic ingredients. You may have to work harder while using a conventional cleaner, but you'll also live longer.
Caution should also be employed if you use a freeze spray to lower the temperature of an overheated component. Freeze sprays can burn the skin and, if inhaled, cause permanent lung damage. Only use freeze spray in a well-ventilated area with a fan available to blow the spray away from your body. Now, let's review the key segments of this program.
1. Electrical wiring is color-coded. The neutral conductor is always white or gray. Ground wires are bare or green. Hot wires can be any other color. But remember, mistakes happen. Always test a circuit before touching any wires. 2. Some modern wiring systems are equipped with ground fault circuit interrupters. Use the test mode to ensure the ground fault protection is functioning properly. Never service a circuit that isn't grounded. 3. The safest way to service electrical circuits or equipment is to use a lockout-tagout procedure. Follow the procedure carefully and remember to test all circuits before touching them. In the next program, you'll look at how to respond when someone is injured by electricity.